here we go. So, this last 2 weeks, my server broke, my laptop broke, my microwave broke, and my car broke. So I've got a new microwave and a new server. Still trying to fix the car, and I don't think I'll get a new laptop at home because I have a computer. So, and this little fella is still going strong.
Wait, what about a bike?
Yeah, I got a new bike.
Oh,
Yeah. But the old bike is broken too. Yeah. All right. Why does metal feel colder than plastic? Yeah. What's so special about a metal? What do we call it? I think I heard the word. It's a conductor, isn't it? So, why does water at 10 Celsius feel colder than air at 1 Celsius? Like, I'd much rather stand outside in 1 Celsius air than I would sit in a bath of 10 Celsius. But why is that? So again, it's to do with conduction, how easy it is to transfer heat. Also, it has to do with how much heat the material can take, right? So like a metal is a good conductor. It means when I hold it, the heat very quickly travels into it, and the metal can get warm very quickly. Yeah. We need another way to talk about heat and temperature. Conductors feel hotter than plastic even though we give them the same heat. You know, if I put 100 joules of heat into this metal, or if I put 100 joules into this pen, it's the same heat, isn't it? But this will feel hotter, even though it's about 100 joules of heat. And this is just reminding you that heat and temperature are not the same thing. Okay. So different materials have different capabilities when it comes to absorbing heat energy. And this gives us our first notion, our first definition, called the specific heat capacity. Does anybody know what this is? Yeah, what would you say it is? Something. Yeah.
Heat
Yeah.
required to raise 1 degree Celsius
Of yeah.
temperature.
Yeah. Of what?
An object or material or something.
You left out one key thing. Just one little thing was missing.
Oh, in 1 gram or kilogram.
Yeah. The specific heat capacity of a material is the amount of energy required to raise 1 unit mass of the material by a unit of temperature.
I think we learned this in chemistry.
With Lorraine?
No.
Yeah, okay. Oh yeah, this would be important for chemistry because it deals with heat and materials. Many students, like Dorian, not just picking on you, but because you're a good example right now, in the exam when they write the definition, they forget to mention the fact that the mass is a unit mass. It's a simple thing to forget, that it's quite common, because everyone remembers the increase of 1 degree. It's just the mass is sometimes forgotten in the exam. You know, when you're stressed and you're sweating and you're looking at the clock and time is running out, it's easy to forget things. Yeah. Right. You got that? Yeah. Oh, so what would be the units for this? So it's the amount of energy required to raise 1 unit mass by a unit of temperature.
Per kilogram per degree.
Yeah. Now we'll have a look at that in more detail when we look at the formula, which is right now. So by using this definition, we can get the formula for the total energy required to increase m kilograms of material by a temperature change of delta theta is given by this formula. Let me just write that down here. So how much heat do I need? Well, how much mass do I have? What's the heat capacity of the mass? And how much extra temperature do I want? So if you look at the C here, you can get the units. So I think that's what the heck, Stephen? That's a theta, sorry. That is joules per kilogram per Kelvin. That's the unit, okay? Right. Oh, like give it a name.
Yeah.
We call it the Zachary. Yeah, actually, it would seem convenient to have a name for it, wouldn't it? Like, I don't know who would have discovered this. See, Joule already has a unit named after him.
Yeah.
Ah, well. Okay, you got that?
Mm-hmm.
Yeah? So let's have a look at some values of heat capacities for different materials. Before I do, let's brainstorm some values. What I mean is, what materials in your home can you think of that would have a high heat capacity? Now, having a high heat capacity means much energy is required to go into it before it'll raise its temperature. Cement, it's kind of medium-ish. Wouldn't be particularly high or low, I think. No, actually, maybe you're right. Yeah, it'd be pretty high, perhaps. What else? Wood. Yeah, I think so. You'll need to put a lot of energy into it before you can warm it up. You're really thinking of insulators, aren't you? Like, what materials are insulators?
Yeah, all the foam.
Huh?
Like the things that you're making porcelain.
Porcelain? Oh,
Yeah, ceramics.
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 Yeah, actually they use as well.
Yeah, I guess so. Yeah. What would have a low heat capacity? What would get hot very quickly in the home? Metals.
Yeah.
Huh?
Frying pan.
Frying pan? Yeah. Yeah. Huh? Where would you say water is? A high or a low heat capacity? Yeah. Yeah. Water is a high heat capacity, which is actually important. Let's have a look at some values, okay? So the first one is liquid water, which is 4181. So, that looks like, you see Zach's bottle there? You see his bottle of water there? I would say that's about 1 kilogram of water, roughly.
Yeah, it's 1 liter.
Yeah, good. It's 1 kilogram of water. So, if I put 4,181 joules of energy into that water, I know it'll be 1 degree hotter. Which isn't really a lot, considering that I put in 4,000 joules of energy. Right? Liquid water is 4181. Okay, continue. Next one. Ice. Now, actually, before I continue, do you think ice would be higher or lower?
Oh, I know that to melt an ice, you put like a torch.
Now, I'm not talking about melting the ice. I'm just talking about making the ice a bit warmer. So let's imagine the ice was at minus 20.
Well, it takes.
And I want to bring it to minus 19.
Yeah, it's
Higher or lower heat capacity?
no.
Or the same? Yeah, that's another possibility.
Ice. High.
Higher than 4181?
I would say so.
No, it's low.
You're lower? Dorian's thinking possibly the same. Gina, what do you think? Going higher? Lynn?
It's low.
Lower? What do you think, Harry? Ice, higher or lower? Lower. Most people are saying lower, which is correct. Now, how much lower? A good bit lower. Near about half. It's surprising, isn't it, Dorian? Because you would think it should be nearly the same. After all, it is the same material.
Same compound.
Anyways, this doesn't matter because in the future there won't be any ice left, so this will just be a hypothetical value.
Well, we will have ice, but only in the freezer.
Artificial ice grown in the lab, yeah. No naturally occurring ice. They were, last week there was, in the newspaper last week, they were looking at a sort of ice mountain in Greenland, like a large ice structure. And they said over the last 10 years, its height has halved. So it went from something like, I don't know, like maybe 300 meters ice cap to 150 meters.
Did you see
Yeah.
Venus?
Yeah. Now I don't know if that's related to global warming or it was just a freak combination of high tide and wind and so
Most
on.
coastal cities will be like that.
Yeah, well, but I think the Venice incident might not be global warming
The
related.
thing about Venice is that they always have floodings.
It's
around
common,
this
isn't
time
it?
of year, yeah.
And the other problem with Venice is it's slowly sinking,
not
which doesn't
sinking.
help.
Well,
It
the
doesn't
biggest-
help.
The biggest forest of I don't know what type of wood is actually in Venice. They have like underneath.
Yep.
They.
Oh yes, no, I
use,
was in Venice and I remember seeing in the museum the pictures of how the city floats, but the wood is sinking slowly into the seabed. Yeah. The next one is gas. Steam. So what do we think about steam? Would it be similar to ice or similar to liquid? Higher or lower?
No.
Yeah, but not much. Not much. Basically the same. Has anybody been to Venice? Yeah. I'm sure it's local for you, isn't it? Practically.
Quite local.
Yeah. I was there years and years ago.
Oh, I
It's
also-
fantastic. It's
The
fantastic.
thing about Venice is that you have to get out of the touristy streets
Yeah,
and then you
yeah.
see the actual.
We stayed on one of the little islands. I can't remember what it's called. Not the main part, but anyways, best thing about Venice is the espressos are €1 and the gelato ice creams are €1. So that's walking around.
Depends on where you have it.
True, but I mean you can get a
Yes,
scoop
that's
of
how
ice
it
cream for €1. Just and it's good ice cream too. Okay. Next one we'll have a look at is copper. Now, look at how different that is compared to water. Huge difference, isn't it? It's only 385 joules required. Okay, next material is milk. Now, I don't know why. I know why I put milk in because I think I did a cappuccino question. So you can see, I think it's kind of interesting that milk is, you would think it might be similar to water, but I think the fat content of the milk changes its behaviour. But I would have thought that having the fat in the milk should make it a higher heat capacity,
Yeah.
because fat is exactly. So I'm doing this to show you something. It's not that milk is strange or copper is strange. It's just because liquid water is so strange. Like that value is unusually high, compared to everything else. The next one is alcohol. Again, you would think it'll be like water, but it also a big difference.
In hydrogen bonds.
The bonds, you think?
Could be.
Okay, good. Yeah. Did you do this in chemistry or something?
Yeah.
What did you learn about
It takes a lot of energy to break the bonds.
in alcohol?
No, in the water.
Intermolecular bonds.
In the water?
Water.
Okay. Lead. Look how small lead is. 129. That means it's extremely easy to warm lead.
It's used for
Yeah.
soldering and stuff.
Is it?
Yeah, nothing.
For soldering?
Yeah.
I don't know. I haven't used it before. I don't know if lead is used so much nowadays.
No, it's just so bad for you.
Yeah.
Vapor and stuff like that.
Yeah. I can't think. I think the only time you would really see lead being used maybe is in hospitals for the X-ray
Yeah,
screens,
yeah.
perhaps.
And then we use it to make like a dome to cover nuclear reactors
Yeah.
and stuff.
Yeah, with concrete, lead and concrete. And lastly is air, which is pretty high, 1,000. Okay, you got that? So can you all understand what I'm saying about how strange water is? It's very, very high. Now that's actually important for us. Does anyone know why it's important that it's so high?
Because we are mainly made up of water.
Yeah, well, but why? Yeah, true, we're mainly made up of water, but why is it important that the water be so high?
To sometimes remove heat from
Because-
different things because this stuff will heat.
Store heat, yeah. But why is that important? Yeah, go on, you're halfway there, nearly got it.
Because we're not cold blood.
Yeah, we're getting closer, yeah. I think Gina and you basically have it. You want to store heat in things that are alive. Because if the temperature was to change outside, you don't want your temperature to change so quickly, right? So like you said, you want to store heat so that you have a lot of energy inside you. If it got suddenly cold, you don't want your temperature to drop by 5 degrees. That would be a big problem, right? So the high value is important for life. This is what makes life possible, that water has such a high value. Yeah, so it needs to be this. So water has all these strange features that make it important for life. Like number one, it has a high heat capacity. I think it's important that it's transparent. It's also important that ice has a lower density than liquid water. Basically, every property of water is important for life. You know, so water is really the material for life. Yeah. Okay. Why do different materials have different heat capacities? Any ideas?
Depends on their structure.
Could depend on their structure, yeah,
The
or
energy needed to break the bonds.
the energy to break the bonds, perhaps, yeah, but not quite, because for when you heat up water, you're not really breaking any bonds, are you? It's not like you're releasing hydrogen gas when you heat up water.
Yeah, but like H2 and then it covers steam.
Yeah, but we're not talking about that yet. We're still thinking just water.
Electrons are just vibrating faster.
Yeah, it's complicated. So there's no simple reason for why different materials have different heat capacities. It's not like, oh, it's because the atoms are bigger or smaller or there's more whatever. It's a bit complicated. We might look at it later. That's actually a dirty lie. We won't look at it later. So sorry. Right, here's a question for us to do. Actually, it's one I want you to do. How long would it take to boil enough water to make a cup of tea by using a small 1 kilowatt electric kettle? And I want you to estimate the value. So for example, firstly, what formulas do you need? You need power equals work over time. What's the power here? 1,000. Yeah. The time is what you want, and what's the work? The work is the heat energy. What's the formula for the heat energy? MC delta theta. Right? Now, wait. Before you calculate it, I want to make sure you have the right values. Estimate the M. What value of M will we have? 250 grams, just about enough for a cup of tea. Yeah? Let's put a little extra in case, we'll make it 300, just to be sure we can get a cup. So 300 grams, right? Now, what's the C for water? 4181, isn't it?
Yeah.
And what is the delta theta?
From
No,
41 to
What temperature roughly is water when it comes out of your cold tap?
it's around
20.
Oh, it is not around 20. Your cold tap?
Oh,
15, 12, something around.
15, I would say 12.
12.
12, yeah. Especially with this type of weather, a cold day, the cold tap might be even 10. So how about we'll say it goes from 10 to 100. So what's the delta theta?
90.
90. Okay. So calculate for me. What time? How long will we have to wait to make this cup of tea? Zachary, remember?
Okay.
Joules kilogram minus 1.
Yeah, joules per kilogram per Kelvin, isn't it? Do we have answers? Give it to me in minutes and seconds. What time are we talking about? What you got, Gina? Oh, give it to me in minutes and seconds.
In minutes?
Minutes and seconds, yeah. Yeah. What you get, Dorian? Not yet, okay. Lynn?
It's 100.
100 minutes?
No,
That's a what?
it's a second.
100 seconds? That seems a bit too quick. I think you might have made a small mistake somewhere. It seems a bit too quick. What you get, Diego? Zach? Okay, Gina? What you get? 7 minutes? Ooh, that seems like kind of a long time for making tea, doesn't it? But we're only using a small kettle. About 7 minutes. Let's have a look. So, we have power equals work over time, which equals mc delta theta over time. So, time equals mc delta theta over power, which is 0.3 times 4181 times 90 over 1,000. How many seconds did you say? Ah, okay. It's not 7 minutes then. Yeah, your small answer was the right answer. That's very quick for tea, isn't it? Well, I suppose we're only using a little bit of water. It's not even 2 minutes. 112 seconds? I'm surprised by that. That's a very short time, but okay, so that's
0.887.
it's about 2 minutes nearly. In real life, will it be longer or shorter than this time? Longer, why?
Because you have like
Efficiency, yeah. Okay, are we all happy with that? So, good job, Lynn. You're the one who got it. What did you do wrong, Dorian? Or you just didn't get it finished?
No, 0.3.
Oh, did you write in 300? Good old 300 kilogram cup of tea. Mm-mm. Party size tea. Okay. Shall we do the next example? Oh, sorry, do you need to? You got this? Yeah? Harry, you got this? Yeah. It doesn't actually matter because it's a delta theta, because it's a change.
so it would be the same.
It would be the same number, yeah. Right. Here's another one for you to try, a little easier. 100 grams of ice is at minus 10. How much energy do you need to bring it up to minus 1? Yeah. Now, be careful, it's not 4181, it's ice, yeah. So what do we get? Oh, and of course, Dorian, it's 100 grams. Okay. Got an answer already? What is it? So it's M, which is 0.1, C, which is about 2000, isn't it?
2001.
Yeah. And the delta theta? 9. And the answer? What is it? 1000?
899.
So nearly 2 kilojoules, right? Roughly this size. Okay. Okay. Continue.
So,
Yes.
if say the question asks for the specific heat capacity,
The definition.
no, what do we write as? Do you need to write in Celsius or Kelvin?
Both are acceptable.
Okay.
But, you know, it's kind of just a good habit to be using Kelvin instead of Celsius. But there's no consequence. And in fact, some books will not use joules per kilogram, they'll use joules per gram. So if you're using joules, if you're using kilograms, then the unit is 4181. But if you're using grams, then it's 4.181. Okay. But to answer your question, Dorian, I think the convention is use Kelvin when possible and use kilograms when possible. Although in chemistry, there's still the tendency to use grams, I think, isn't there? Like with Lorraine, you're probably only using grams. Yeah. You haven't done any question that needs to mention the word gram yet. That's I can't believe that. Really? Yeah. Have you talked about moles? No.
No, probably next time.
Okay. Right, next example. Here's another hard one for you. An electric, so it's a bit like the kettle again. An electric heater has a power rating of 3 kilowatts, 3000 joules per second. It's used to heat a room, and the room is 10 by 10 by 5. The room is at 10 Celsius, and you would like the temperature to be 20 Celsius. Assume the density of air is about 1 kilogram per meter cubed. It's not, it's a little bit more, but just roughly 1 kilogram per meter cubed. How long would it take for the room to reach the temperature? Okay, so this is a little bit like the electric kettle, but it's a bit more complicated because you'll have to calculate the mass of the air. What formula would give you the mass of the air in the room? Now you know the volume of the room, don't you?
So,
And you know the density of the air, don't you?
so just 10 times 10.
Yeah, density equals mass over volume. Right, I'll give you a minute, see if you can crack this one. Give me the answer in minutes.
Minutes? 28.11.
Could be that, yeah, let's have a look. So, power equals work over time. So time equals work over power. Work is mc delta theta over power. And then let's use our friend density equals mass over volume. So what does mass equal? Density times volume, doesn't it? So that's density, volume, capacity, delta theta over power. Now let's put in the numbers. What's the density? 1. What's the volume? 500. What's the C? 1012. What's the delta theta? 10. And what's the power? 3000. So what is that in seconds originally?
1686.67 seconds.
So that is how many minutes?
28.
Divide by 60?
Mm.
What you get?
28 minutes.
28 minutes?
And
Okay, it's about 28 minutes. In other words, you're talking about a size of half an hour. Half an hour. Yeah, this is the scale. But again, in real life, will it be this amount of time? No, in real life, it'll probably be more closer to an hour than closer to half an hour. You know, you're going to lose a lot of heat where? It's going to go out the window, it's going to go into neighbouring rooms, it's going to go under the door, you know, so in real life, maybe the efficiency is only 50% and it'll take you an hour. Yeah. Depends on the room, doesn't it? You know, like a room like Cav will probably take 2 hours because there's so many ways for the heat to get out of that room, okay? Whereas this room is probably not too bad. I mean, those windows are pretty good. They're not too bad. They seal pretty tight. You know, it's not cold outside there, so maybe 45 minutes in this room. A physics student is making a latte. He mixes 200 grams of hot milk at 27 Celsius to 50 grams of hot coffee at 80 Celsius. We assume coffee is kind of like water. It's not, well, it's not too far away from it.
Wrong temperature of milk to be a latte.
Are you sure? Because I looked this up. I thought it was 80 Celsius.
Yeah, but you don't put cold.
Is this where we discover you're secretly a barista? Is it?
Yeah, you don't put cold milk into the hot coffee.
But I didn't.
27 degrees.
I mixed 200 grams of hot milk at 27. Oh, okay, right. I get what you're saying.
Around
If-
like 60,
Yeah, well, look, it's only a student, not a barista, so.
I've actually done a barista course.
Good man yourself. Do you work here?
I can't. It's student visa.
Oh, rats. Well, that's okay, you can make us lattes.
Yeah.
Yeah.
Cool.
Where's the coffee machine? Where's the coffee?
I don't know, that's your problem, man.
Yeah, come on, get a little trolley and bring it around. Okay, all right, Mr. Barista. It's not technically a latte then. A physics student's making a milky coffee. How about that? Okay. He mixes 200 grams of hot milk at 27 to 50 grams of hot coffee at 80. What is the final temperature of the milky coffee? So this one is a little bit different to the other two because, well, actually, maybe you can tell me what is so significantly different about this problem compared to the previous problems.
Two different.
Firstly, there's two different materials, correct, and what else? Two different masses, two different temperatures, two different capacities, what else? And combine them, yeah, and what else? One thing is missing here that the other questions had.
Changing
Not quite.
No, they didn't say the specific
the
one.
volume.
No. No. What's this missing that the others have?
The hot power.
Yeah, so in the other examples there was something providing heat energy to the system. A heat pump, like the electric heater or the electric kettle or the sun for the ice cube. But in this example, that's not the case. There's no energy being put into this. It's not like he puts the cup of coffee onto a heat source, right? All he's done, he has the coffee, he has the milk, and mixes it together. There's no heat going in. Do you understand? Yeah? So this problem is done a little bit differently. Watch carefully. Let's draw a picture here. So, how much coffee did I say? 50 grams. And then on top of that he pours 200 grams. Now this is at 27 Celsius, and this one we said is at 80 Celsius then. Okay? And then you pour, and then you mix them together. Right? And then at the end, what you'll have is this. Even though they're mixed together, in your mind, it's easier to imagine the coffee and the milk don't mix together. This is a little tip, okay? Stephen tip. It's easier to picture the milk and the coffee still separated, even though they are mixed together. We'll imagine they're still separated. So this is 200 grams of coffee, and it's 50 grams, 200 grams of milk, 50 grams of coffee, but they're both at, we'll call it X Celsius. Do you understand? Yeah. Now, this is how you do these problems. The milk, is it gaining or is it losing? It's gaining. And the coffee is losing. Now, here's the idea. Because no heat is being provided from the outside, it means the gain in energy of the milk came from the loss in the coffee. That's the concept here. It's a transfer, yeah. In other words, this is a version of our good friend, the most important rule in physics, conservation of energy. That the energy left the coffee and entered the milk. Right? So, let us look at the coffee. The milk. What's the M for the milk? 0.2. What's the C for? Okay, actually, before I write that down, I'll just say delta Q gain for the milk will equal delta Q lost in the coffee. Yeah, no, sorry. That's a bit of a Trump's mistake. Okay. Right, what is the M for the milk?
0.2.
0.2. The C for milk, what did I say was? 2?
2850.
Okay. Now, please be very careful. What is the change in temperature? And we like to keep it a positive number. So it starts at 27, and does it increase or decrease to x? Increase to x. So what would be the delta theta? No, it'd be x minus 27. And this should equal, for the coffee, which is M, C,
which is water.
roughly water, yeah.
181.
And now, again, carefully, what's the delta theta here?
80 minus 80.
No,
X minus
I want to keep it positive, so it's not it's going from 80 down to x. Oh, sorry, did you say 80 minus x?
Yeah.
Apologies. 80 minus x. Sorry. Okay, can we solve for x? Yes. X should be some number more than 27, but less than 80. Obviously, it's in between. Okay, I'll give you a minute to solve this. My tip, maybe to make your life a little bit easier, is first multiply these two and first multiply these two. Make it a little easier. Yeah? Okay.
Your calculator can do it in.
Did he just type the equation in?
Yeah.
I just put solve brackets, the whole thing.
You're a lazy ass.
I mean,
So and so.
You'd be
What
allowed
is it?
to use that calculator in the exams.
Yeah, but you don't get marks for not. If you just have the
I just have
answer,
to show the things,
if you just show the answer, you don't get the marks.
But I know on the
Yeah.
what is it called, the NCUK guidelines, it says you only allowed a specific approved calculator.
Yeah, and those so and so's. When I asked them to give me a list of approved calculators, they wouldn't. And then when I said, "Can they use this calculator?"
This one.
Well, whatever one at the time, I can't remember. They said something to me like, "You seem to be confused. Would you like to come to Manchester for training?" I'm like, okay, just leave me alone. So they're not giving me guidance, so I don't care. Whatever calculator, they're not going to give me a list of what calculators can and can't use. That's their business. So if you want to use a graphing calculator, that's fine. They've never told me no, students can't use graphing calculators. So what is the x here?
X is 41.2 per unit.
That's a really cold cup of coffee.
Ah, no, 41 isn't too bad, is it, for a cup of coffee? A milky cup of coffee?
It's the one you can drink without like burning.
Yeah. 41 seems like what, do you only drink coffee at 200 Celsius, is it? Or
No, I don't drink coffee.
you're a barista who doesn't drink coffee? Interesting. Where'd you do your course?
Johannesburg.
And how long of a course was it?
It was a week.
Like how many hours do you think that was total? It was a full day?
Yeah.
Okay.
9 to 4 usually.
Okay. And were you doing like fancy designs
Yeah.
and the...
No, we didn't really do latte art. It's kind of difficult
Yes.
to just learn.
There's some amazing latte art out
Yeah.
there. Like really cool stuff. So did you work anywhere afterwards?
No.
So you got this barista course.
And then I decided to come to Ireland.
Ah, okay. And you can't work here
Yeah,
officially.
yeah.
Yeah.
But I'll get
You can get a different visa.
No, you will cancel your visa if you work on
Ah.
a student.
That's unfortunate because if you're qualified as a barista, it'll be very easy for you to get a job in Dublin.
Yeah.
Because there's most coffee shops, you know,
So
they're always looking for
Yeah.
baristas.
I don't have experience. So,
yeah, but you have the course,
yeah.
so they would be happy with that, I'd say. But anyways, you can't do that legally, anyways.
Why can't you work like even a minimum amount of hours, like 20 or something like that?
Oh, the immigration office here is so confusing. Sometimes they give the students a visa for working when they're not supposed to. Officially, they're not supposed to, because your course here is kind of like some, I can't remember, whatever name they have. It's like almost like a high school
Okay.
name. You know, like it's not the same thing as a student coming here for college.
University.
Yeah.
No degree.
Yeah. Oh, so actually, I suppose you'll have a different visa when
I
you're
don't
at.
have a visa.
You don't, but you'll have a different visa when you're here for university. It might let you work. I don't know.
No, it's the same.
Is it the
Just
same?
student visa.
So you can't even have a part-time job when you're at university.
Yeah.
That's true.
They
No,
got like
there's
one is two.
over here.
Well, do you know what the other problem is? I think it might depend on your country too, as well. I don't know. This might be another factor. Why does your visa let you work here?
No, not right
No.
now.
But do you think next year it might?
I don't know, because Emer, there were students asking about it, and Emer said that when you get into university, then you can get
Yeah.
a work permit.
That's what I thought.
Yeah,
That's what I thought.
One of
Because
those
we don't have the
20,
degree.
20 hour
Yeah.
week
something like that, yeah.
thing.
Max 20.
Max 20.
Yeah.
40 for the holiday.
Yeah,
Although
that's
I
good.
have a feeling a lot of students just work for cash in hand at like a family restaurant of an uncle that they have here or something. Do you know what I mean?
Yeah.
Like I've had plenty.
Underground.
I'm sure I've had plenty of Chinese students who have said, "Oh yeah, I work at my uncle's Chinese takeaway, you know, as a waitress or a waiter or whatever." That has to be pretty common here,
I
right?
think that is a lie.
You think it's a lie?
Yeah, it's illegal. Or,
Oh, it is illegal. That doesn't mean the students aren't doing it.
The thing is that it's really hard to prove that someone is doing that. So.
You'd have to catch them doing it. Yeah. Immigration
Even
bust.
so you can just say like, no, I was just like, I don't get paid. It's just like. For
yeah.
If
For
South
helping.
African police had to deport every single
Illegal.
worker there, we'd lose half the work.
Okay, alright, yeah. We're not that bad here, yeah. Right, now here's another question. This is very much an exam type of question. You have a 10-gram lead bullet traveling 100 meters per second and it hits a wall. So the bullet, you know this from movies, when you see bullets hit zombies and steam comes out of their corpse. The bullet is warmer. Why is it warmer?
Because of the friction with
Kinetic energy.
The kinetic energy, yeah. What's happened? The kinetic energy has converted into heat energy, hasn't it? Yeah. So the bullet will be a little bit warmer now. I would like you to calculate how much warmer will the bullet be.
Does this mean the bullet stops when it hits the wall?
Usually bullets do stop when they hit the wall.
Some of them penetrate, and then.
Okay.
Some bullets can go through 4 walls.
I think so.
Those big
Yeah.
ones, those round ones.
This is a lead bullet, so it's going to be from like the 1900s, you know, so it's not going through any wall. You know, this isn't like a sniper rifle bullet made out of titanium.
Like a,
Yeah. This is like a 1900 revolver lead bullet.
shot by Napoleon Bonaparte.
That's a bit.
So all the kinetic energy.
All the kinetic energy has become heat.
50.
What did you get? You got an answer? Pretty big, isn't it?
Really, really big. I don't think so.
Well, what did you get? Did you get like 500?
No, it's because you made the mass 10 kilos again. I'm telling you.
No, I made it 0.01.
Yeah, that's right.
Problem.
Should be a big enough number. You have it, Glenn, good, yeah.
Cheer.
What did you get, Zach?
I got the.
-1 Kelvin, is it?
3?
3? No, it's got to be more than 3. You said it was like about 50 or something, didn't it? Oh, come on, I thought this was a straightforward one.
Wait.
Okay.
No.
Guys, you're making me worried. Got an answer, Harry? What you get? 25.9?
35.
38.8.
Ah,
38 point something.
okay. A half mv squared
It's 38.8.
equals mc delta theta. You didn't even need to know the m, technically. But it's fine if you did. So you have v squared over 2c equals delta theta, which is 10000. What's the capacity for lead? 129, is it?
29.
So what is this?
38.76 or 38.8.
Increase of about 40 Celsius. So that's the increase, okay? But let's finish this question by working out what the actual temperature of the bullet is. So let's think about this logically, okay? You take the bullet out and you push it into your gun and you swing it around and you fire it, okay? So what would be the temperature of the bullet at the beginning? Should be about the same temperature as your hand. Well, I wouldn't say be ambient temperature. Ambient temperature is room temperature. I would say it's the temperature of your hand. What's body temperature? 37, isn't it?
36.5%.
So okay, we'll just say it's about 37. Yeah. Well, it doesn't matter. Roughly 37. Maybe you have a fever or whatever. 37 plus the 38.8. Okay, so what's that about? Roughly 72? Well, what's that, please?
75.
But when the gun explodes or when it's fired, wouldn't the explosion impart more heat energy on it?
That's true, actually. So if anything,
And then
This-
when it's traveling through the air, it would lose.
exactly. So it would gain heat as the friction.
Yeah, the friction of the air.
Yeah. So if anything, this represents a minimum temperature because, like you pointed out, there are other things adding to the temperature. So the bullet's temperature is at least,
So
what you
that's
say?
before firing.
75.8 as a minimum. As a minimum. But
So that's before firing.
which?
That temperature.
The 75? No, that's at the end, after it hits the wall. What I'm saying is, I'm imagining the bullet started at 37, it hits the wall, it warms by 38, so total is 75.8 then. But as you pointed out, Zach, it's probably more than this because the explosion probably warms the bullet more than 37 at the beginning.
Definitely.
Well, definitely, yeah. And as it's travelling through the air,
It would lose heat.
it'll get some air friction heat.
I think it would lose heat though, as it moves through the air, wouldn't it? Yeah.
But you also have the friction.
Friction though, friction. It's cutting the air. Yeah.
Because it's actually like a ball, so it's not really aerodynamic.
Yeah. I'm sure the friction from the air has to warm it up because it's really pushing through the air hard. Or maybe not. Maybe the air friction doesn't give it much. You don't think so?
Just that small.
At what speed would it go?
Unless it's a really long distance.
Oh, 100.
Yeah, I suppose so. Okay, you take the gun and you hold it right in front of the wall. Right?
No friction.
No friction then. Yeah. Do you know, because in my head I'm kind of thinking that maybe with the explosion it could be even more than 100 Celsius.
Yeah.
You know, because you shoot a zombie and you see steam coming out. So that kind of means it must be at least 100, right?
Yeah.
In real life. Well, zombies, not quite real life then. Okay. Right. Finally, we need to describe an experiment to calculate the specific heat capacity of a solid or a liquid. Okay? So this is something you might need to know for an exam. Let us do the liquid one is the easy one first. Let's do that. So how would you find the specific heat capacity of a liquid? That's actually quite easy. What would you need?
Heater.
You would need a heater,
Thermometer.
a thermometer,
And a recipient.
whoops, sorry. What's it? Thermometer? I can't spell thermometer right now. Is that right?
Yeah.
You also would need some insulated flask of some kind to hold the liquid. Insulated flask. Is that how you spell flask?
Sauce.
Flask. Insulated flask. There we go. What else do we need? Heater, thermometer, insulated flask.
Probably
No, I think that's really it. And of course, you would need 1 kilogram of the liquid.
or you need something to measure how many watts the heat is.
Oh, sorry, yeah. Well, I suppose the heater, you would just need to know,
Power.
yeah, of known power, like with the electric kettle. So here's the experiment.
What's the best insulator?
Oh, maybe you make this out of some kind of polyester or what would be a really good insulated, like a what are those flasks called?
Thermos.
Thermos, yeah.
Those are made out of crystal.
Yeah. It doesn't really matter for the exam. Just tell them that you're using some really well insulated material. So it has a lid on it as well. Okay.
Yes,
So we'll put a lid on it. Oh, my picture. Sorry. Let me just draw this again. Okay. Sorry. Right. Inside is the liquid, and here's the thermometer to measure the temperature, and then we'll put the lid on. Oh, we'll put the lid on it, and also we need to put inside of it. Sorry, I should have stuck a little hole here. We'll put the electric heater inside as well, like this. Oh, golly! Right, there's the heater. Okay, so that's, you should really label this in the exam. So that's the thermometer. That's the heater.
Would they expect us to draw it down?
No, but I like to because it helps focus my mind. That's the liquid. And that's the flask. So what would be the easiest way to do this experiment? Well, I suppose the easiest thing to do would be to time
How long?
how long. Oh, so actually you need a stopwatch as well, wouldn't you?
Or a heater with a timer.
Or a heater with a timer. Time how long it takes to see a +1 Celsius change, right? And then how could we get the, and then call this T. Okay, so if we look at our formulas, we have power equals work over time, which equals mc delta theta over time. What's the m? 1. What's the c? What's the what else do we know? Delta theta 1. So this is actually just equal to c over t. So therefore, the specific heat capacity will equal the power of the electric heater multiplied by the time. There you go. That's the simplest experiment I can think of to measure the heat capacity of a liquid. Oh, okay. I suppose we also need to measure 1 kilogram, so we better have some kind of weighing scales too, shouldn't we? Yeah. So therefore, that. No, there's hidden units here because there's actually a 1 and a 1.
Oh, yes.
Yeah. Now, do you have to use a kilogram? No. But then if you don't use a kilogram, then for the exam, you want to make your life as easy as possible. So you imagine the easiest possible experiment to explain. Yeah? Okay, once you have this copied, because you might have to produce this in the exam, we'll look at the final experiment, which is how to do it if you have something like a solid.
A sensor or something.
Oh, we're not going to use any fancy sensor equipment, Mr. Graphing Calculator. We'll keep it old school. This is how I remember it in high school. We used to use a little electric heater. I think the electric heater we had, it actually displayed how many joules was being consumed. So you didn't actually have to do power multiplied by time. The heater actually said how many joules has been outputted. So actually you could have made this a little bit easier by saying use an electric heater with a energy display, and then the specific heat capacity just equals whatever the energy display is. Yeah. Can we go to the next one? Yeah. So the next one is a little bit harder. It's for a solid. You can't really do the same thing with the solid. You can't just stick it on an electric heater. Well, depends on the solid. So let's not do this then. So for this one, let me think what we need for this one. I know we usually have some ice, I think. Yeah. So, again, what you need here, so I won't write all the equipment down again because it's the same equipment. You need an insulated flask, you need a thermometer and all that type of stuff. So what you do, you have your mass here. Let's keep it easy again. Let's just say we have 1 kilogram again of the mass. And you put it on top of some ice. And you leave it there until you're sure that the 1 kilogram has reached the same temperature of the ice, which of course is 0 Celsius. Sorry, the ice is in, yeah, let me draw that better. Ice plus water. What temperature is ice and water mixed together at?
Well, the temperature of the ice or the temperature of the water?
The mixture. You mix it together, and stick the thermometer in. What temperature will it say?
The water will decrease.
Yeah, so what will it say? Yeah. If I put some ice into Zach's water and mix it really, really well for 5 minutes and put a thermometer in, what will the thermometer say?
If the water before was at like 10 degrees, it would be at 5 something.
No. 0.
0.
Yeah. Because if you mix it together, the ice and water will become the same temperature. The only temperature...
Water freeze then.
No, because just because water is at 0 doesn't mean it'll be ice. We'll talk about that in the next lesson. It's not like once the water hits 0, it suddenly becomes ice. And it's not like when the ice hits 0, it certainly becomes liquid. Anyways, for this lesson, all you need to know is that this will be at 0 Celsius. Okay, and then what you do here is you heat this until you get the water to boil. So there's steam coming off here. What temperature is this at then?
100.
Oh, must be going at 100 then. Okay, so what you do is you put your 1 kilogram into this and mix it around, and you leave it for 5 minutes. So you know what temperature this is at. No, here.
Oh,
It's 0, yeah. So then what you do is you turn the heat off and then quickly, very quickly put this in here. Okay? So I'll write down the steps.
oh.
So firstly, place the 1 kilogram in the ice water for, let's say, 5 minutes. And then number 2, turn the heat off in the boiling water. And then quickly transfer in the 1 kilogram. Okay? Yeah? And then what you want to do at the end is measure the final mass and temperature of this guy here. Now we'll see how that will give us the heat capacity of the solid. I hope I did this right. We'll find out. You can have a picture what's happening. You put the mass in the ice water, it reaches 0, then you quickly put that into the 100 Celsius water. What will happen to the water? Will it get hotter or colder?
Colder.
It'll get colder. The heat energy lost from the water will equal
The heat.
heat energy gained by the 1 kilogram. Yeah? Can we go on to the calculation part? So let's have a look. So
It's just like the coffee and the milk thing.
it is, yeah. What I'm going to do is I'm going to call the final mass big M and the final temperature big T, whatever those numbers are. Okay. How much energy does the water lose? That will be M, which is big M minus 1. Now why did I do that?
Because it's the 1 kilo.
Because at the end when you weigh it, you want to take away the 1 kilogram. Now I know you have to also have the container as well, you know, so I'm really keeping this simplified just to give you the idea. Okay. The C. Okay, do you know, actually, do you know what? No, let's not complicate our lives. I'll just say the mass of the water. Can you know the mass of the water? Easily. You know the big M, and you just have to subtract 1 kilogram and the mass of the container, the flask. Yeah? Okay, C, 4181. And delta T will be 100 minus the final temperature. Yeah? That will equal M, which is 1, C, which we don't know, and then what's the gain in temperature? T. That's nice, isn't it? So that means the C will be mass of the water, which is the total mass, minus the mass of the flask, minus 1 kilogram, times 4181, times 100 minus T, all over T. So by using this calculation, you can get the mass of the solid. Now you realize, if the mass, let's say the mass wasn't 1 kilogram, let's just say it was m kilograms. And we don't have to change this formula too much, do we? What's the only thing that gets changed in this formula? The 1 just becomes an m. Isn't it? So it's no big deal. It was kind of nice in the last one to use 1 kilogram because it just makes this final one simpler. But even if it wasn't 1 kilogram, let's suppose here it was m, then that just means in this formula here, what you divide by m. You know? It's no big deal. Are we okay with this experiment? Yeah? Now, they sometimes ask you to describe one of these experiments in the exam. They might say, describe an experiment to measure the heat capacity of a piece of wood. Describe an experiment to measure the heat capacity of milk, whatever. You know? What's important for me is not that you remember this perfectly and then write it perfectly, because this isn't perfect. What's important for me is that you remember the idea, so then in the exam you can write it in your own words, explaining the steps. Do you understand? So I'm not going to be upset if you don't say flask and you say container. You know, using your own words. Yeah?
Why do we need to put 1 kilogram of ice into the water?
Oh, sorry. So there's not a kilogram of ice. It's just some ice. You
Yeah,
want to guarantee that the water and the ice is at 0 Celsius. If I have some water and I put ice in it and I mix it for 5 minutes, I'm guaranteed my result will be 0 Celsius.
But ice is 0 Celsius.
No, ice can be less than 0 Celsius.
Oh.
But when it's mixed with water for 5 minutes, it will definitely be 0 Celsius. Yeah. It can't be more than 0 Celsius. Why not? Because then the ice would have melted. And it can't be less than 0 Celsius, because then all the water would have become ice. So this is a nice way to guarantee having 0 Celsius by mixing ice with water. And then a nice way to guarantee having 100 Celsius is to have boiling water. But it's important that the top is open. Why is that? Because you don't want any heat from the steam, which will be more than 100, getting in. Yeah? Are we okay with this? Yeah?
But then, if you have it open, doesn't it mean that also some heat will conduce because of evaporation?
That's why it's important to do everything quickly. So you turn the heat on and it's bubbling. Then you quickly turn it off and put the block in and put the lid on. Yeah? Because like you said, if you left it open and you turned the heat off, then you're right, the heat will start leaving the system. Now there's still 5 minutes left, so we've got a heck of a lot done. For the last few minutes, just have a look at some of these questions. But what?
How?
I thought it was working on some of your devices, isn't it?
Mine,
Links only.
mine it works, but
Only?
it doesn't display the...
Really? Well, not to worry. I have it here. I'll display it.
Yeah, it's like that.
Oh. Oh.
It's 22 questions.
There, no. Okay, look. All I want you to do, let me just... wait. I've got a good idea. Just in case, fingers crossed though, just in case I don't get my server fixed tonight, I'll scroll slowly down so you can watch the video later and get the questions, okay? Ask question 1. No, question 2. That's question 3. That's question 4. That's question 6. Eight. 10. Okay, that's enough. So if the server's not working tonight, you all listening? If the server's not working tonight, you can watch the video and there's a few questions for you there to do. Before you go now for your lunch break, I just want you to do question 1 here.